Good morning, class. We are looking at elementary statistics practice test number 2, covering module 2, chapters 4 and 5. Here's chapter 4, probability. Chapter 4, probability, we have some definitions: a simple event, a sample space. So a simple event is an outcome or an event that cannot be further broken down into simpler components. A sample space is the set of all possible outcomes or simple events of a probability experiment. If two events are mutually exclusive or disjoint, the probability that both will occur is 0. So events A and B are disjoint or mutually exclusive if they cannot occur at the same time. That is, disjoint events do not overlap. Therefore, the probability of A and B, or the intersection, this is the notation for the intersection, probability of A intersection B is 0, because A intersection B itself can't happen. It's an empty set. I want to make sure we distinguish between this and 0. This is phi, which represents an empty set, nothing in common. The probability of an event is always between 0 and 1. Probability of A is defined as n of A over n of S, is the probability of event A, and it's always between 0 and 1. Can it be 0? Yes. Which is called an impossible set. Can it be 1? Yes, which is called a sure set. But it can never be negative or larger than 1. The sum of probabilities of all final outcomes of an experiment is always 1. The sum of the probabilities of all outcomes in the sample space is 1. Summation of P sub I, that means the probabilities, is equal to 1. The only time it is not 1 is due to round off error. Okay, if we are changing an exact answer to a decimal representation, it may be that it's not going to add up to 1, but will be very close. As an example, when we look at an experiment of rolling a die, which is a fair die, 6-sided, we have the following numbers: 1, 2, 3, 4, 5, 6. So the sample space for the common die that has 6 faces, we usually call the faces by their numbers, 1, 2, 3, 4, 5, 6. The sample space is 1, 2, 3, 4, 5, 6. A simple event, any individual number such as 1, 5, or you name it. A compound event, any event having more than one outcome, such as odd numbers, which has 1, 3, 5, 3 outcomes, 3 outcomes. The number of combinations of n items selected n at a time is, well, let's discuss a couple of things. Permutation. Can somebody read the definition of a permutation and combination for us?
Permutation is an arrangement of objects in a specific order. Order matters. Example, the letter arrangements of ABC, ACB, BAC, BCA, CAB, and CBA are all counted separately as 6 different permutations. When n different items are available and r of them are selected without replacement, the number of different permutation order counts. As in n probability r equals n factorial over n minus r factorial. Combination is a grouping of objects. Order does not matter.
Perfect. So this is NPR, and that represents the permutation of n different objects. Pick R. For the combination, we use n factorial. So n combination R, n factorial over R factorial times n minus R factorial, or just the permutation divided by R factorial. As far as the combination is concerned, we may use parentheses n comma R, or in this format. So there are 3 formats, and all of them represent combination. So we want to use this where n is n, and we want to choose n that means even R is n. So in this formula, both of them are n. And what happens is that this becomes a 0 factorial, and 0 factorial equals 1. By the definition of a combination, it becomes 1, and sometimes they just say by choice or definition, and the answer is 1. The number of permutations of n items selected 0 at a time, so we are going to use this formula with replacing 0 by R by 0 in this formula. By the way, it means n times n minus 1 all the way to n minus 1 plus R, that's R items. So in this example, since the denominator is also n factorial, so the ratio is 1. So both of them end up being 1, but here's the justification for that. A pizza parlor offers 10 different toppings. How many 4-topping pizzas, assuming we are using different toppings, are possible? Well, you have to recognize whether order is important or not, and order is not important, because if your first choice is, let's say, pepperoni, or it's the second or third or fourth, makes no difference. As order is not important, we use the combination, and in this case, n is 10 and R is 4, everybody. R is 4, so we're going to stick with that. Now, of course, as long as you have this one, you are telling your reader the methodology you're using. You can use a calculator and come up with the answer. But if by any chance you're doing it by hand and you want to simplify, the methodology is very simple. This one becomes 6 factorial. And to simplify that, since 6 is larger than 4, we're going to write 10 factorial as, let me show you how we can simplify this. We can write this as 10 times 9 times 8 times 7. And when we get to 6, we stop and we make it a factorial. They cancel each other. And then the 4 factorial is 4 times 3 times 2 times 1. As you can see, 4 times 2 equals 8. Number 3 goes away, and 9 changes to 3, right? So 10 times 3 times 7 is 210. So you can even do it by hand. Not that you have to, but You have to know the process in case. How many 6-letter code words can be made from 26 letters of the alphabet if no letter can be used more than once? In the code word, in this case, order is important. We are making up a code. So it is using the permutation. And in the formula of a permutation N, we have 26 letters to choose from. How many are we choosing? Only R equals 6. Now, of course, this is 20 factorial. And it's the same as writing 26 all the way to 21. And then the 20 factorial cancels out. So you have 26 times 25 all the way to 21. And you come up with a huge number, 165,765,600. But this is the key, everybody, to showing your reader you understand. And the rest, you can use a calculator. This what gets you full credit. A quiz consists of 3 true-false questions. How many possible answer keys are there? Write out the sample space and the tree diagram. Well, here's the formula I want to tell you. N of S, S is the sample space, is the number of outcomes per stage and raise it to the power of number of stages. Remember, each stage, that means each true false, has only 2 outcomes. How many stages, how many questions do we have? 3 questions. So the answer is 2 cubed, which is 8. So again, each stage in this case refers to each question, which is true, false, giving us 2 outcomes. And there are however many questions. So we can write it in this fashion. It's important to understand the concept of a tree diagram. Okay, you have the branches, and when you use the branches, you want to be consistent. If the top one represents the true and the bottom one represents the false, you keep it the same. So this is your first stage or the first question. Question number 1 is your first stage. Question number 2 is your second stage. And question number 3 is your third stage. So the first stage, there are 2 outcomes. Now for here, at the top you have T, at the bottom is you have F. For this one, T and F, and this one again, T and F. So this results in T, 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 meaning those 3 questions, what if we picked all of them correct? We have true, true, true. But this one would be T, T, F. This one would be F, F, F. This one would be F, F, T, and so on and so forth. If you write out all of them again, the very top one is all T, the very bottom one is all F, and in the middle, you should be able to figure out the rest. There are 2 cubed or 8 outcomes. The sample space for tossing 5 coins consists of how many outcomes? Write out the sample space. Well, N of S is the number of outcomes per stage, and we raise it to the power of number of stages. And clearly, in this case, we should recognize that we have coins, okay, heads versus tails. So there are 2 outcomes. for each coin. How many coins? However, they have given us 2 to the power of 5, that's n of s, which is 32. Don't mix it up with 5 squared, which is 25. So 2 to the power of 5 is 32. So if we were to draw, this is what's going to happen. You have 3 diagrams. First, I'm going to show you for 4 coins because of the limitation of space, everybody. Limitation of the space. The first one is H and T. The second one, keep it the same. The top branch is H, keep it as H. The bottom is T, H, T, H, T. And here's the third one. Here's the fourth one. Stage 1 is the first coin. Stage 2 is the second coin, the third coin, the fourth coin. And we're going to add one more coin again because of the limitation of space. I'm doing that. So I'm going to show you again HT. So if you look at the top one would be H, 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 H. There are 5 of them. Okay. And of course, this one would be H, 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 T. If you look at the bottom one, stage 5, the last one would be T, 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 and then there is another T. So look at the very first one, all H's, and the very last one, all T's. So pretty straightforward. I hope everybody can follow that. We're going to move on, everybody. Could somebody read the question, please?
A random sample of 100 people was asked if they were for or against the tax increase on rich people. Of 60 males, 45 were in favor, and of all females, 22 were in favor. Write the contingency table and answer the following questions. If one person is selected at random, find the probability that A, this person favors the tax increase on rich people.
Excellent. So we have to write the table. And here's how we write the table. This is called the contingency table, which have several variables. We have males and females. Those who are for tax increase, so those who are against it. What I've done, I'm using specific variables. For males, I'm going to use M, females F. Those who are for the tax increase, T. Okay, so set of T, if you will, and those who are against it, I'm going to use A, just to make it easy for the next step. So we have a random sample of 100 people. So that this last row and last column would be a total. This is the grand total. This is how many people we have. When we continue, of 60 males, 60. How many are in favor for tax increase? So we plug in 45. So I'm showing you how to fill up this table. And all females, and we don't know how many, 22 were in favor. So this is 4 or in favor, 22. So we put it here. When they say write the contingency table, now we're going to finish this off. It's very simple. If this is 60 and this is 45, what do you think we should put here? Anybody? What number would go here?
15.
50. That's very simple. because they must add up to 60. So if you put 15 here, okay, for example, here, if I have 60 here, what number goes here?
40.
Because they must add up to 100. Okay, so go back here, 45 and 22, the total of 67 goes here. You see that, class? Now, if this is 67, I'm going to subtract it from 100 and I get 33 here. And if I got 40 here, I subtract 22 from 40 and I get 18 and I can figure out the rest of them. So the rest of them are very straightforward, everybody. Okay. Now, this person favors the tax increase on rich people. Whenever you're dealing with a probability, it's either simple probability or known as marginal probability, in which case the sample space is the total size. And in this case is 100. Whenever I want to do probability, I always start with the sample space of interest. I always start with the denominator. So the denominator is 100, but how many are in favor? Then we look at the number that are in favor, which is the sum of these two, or 67. However, symbolically, we're going to write it as follows. So n of t over n of s equals 45 plus 22 over 100, or 67 over 100. All right. This person is a female. Well, again, as I mentioned, n of f over n of s, the denominator is the first one I like to go with. It's 100. N of f, you look at the f, 22 and 18, 40. Now, of course, 40 over 100, it's 2 over 5 or 0.4, depending upon how they want you to write it. As a fraction, you must simplify it, but you show your work from here to there, or if you want to go with a decimal or percentage according to what they ask you. This person opposes the tax increase on rich people, given that the person is a female. If this person is a female, she opposes the tax increase. I wrote this in a parenthesis, meaning maybe this expression is given in this format. So the two phrases are the same. So first, I want to remind you of conditional probability. Probability of A given B is probability of A intersection B over probability of B. Probability of B given A is probability of A intersection B over probability of A. That's a formula. You have it in your formula sheet. And this line segment is read given. Now, if we were to write this one, we would write probability of A given F. Because given, after the line segment comes this, which is probability of A intersection F over probability of F. When you go through the process, it simplifies to N of A intersection F over N of F. I want to make sure we understand this one, because if you understand this one, every conditional probability, which means somehow the given is embedded, becomes easy. I always start with the denominator. Remember, your original sample space is the total size of 100. The moment you see given, your original sample space is no longer there. It's a smaller one. So this is no longer the denominator because of this conditional probability. So what comes after given, in this case, females, that would be your new sample space. So N of F, which means 40 is your new sample space because you no longer deal with the whole, but rather only with this group. So the denominator is 40. Now, A intersection F. A intersection F. So this one and this one, what is in common? 18. 18 over 40 is the answer. You simplify it to 9 over 20 or 0.45. The person is a male, given that that he favors the tax increase on rich people. In other words, again, we no longer are dealing with the total sample space of 100. And if we were to go with the formula according to this, we have probability of M male given what comes after given T. Those are in favor, which is probability of M intersection T over probability of T, N of M intersection T over N of T. Again, as I said, I like to start with the denominator. So what comes after the given? Those who favor the tax increase. Therefore, the total size, those in favor, 67 is the new sample space, is the new denominator. Out of those, after that, out of those that are, so the denominator is 67, that are in favor, how many are males? So in this column, how many are males? 45. So the answer is 45 over 67. And again, when you change it to a decimal notation, this is what I mean. When it happens that we change it to decimal notations, it is not an exact answer in this example. And that's why the probability when you sum them up may not become identical to 1 just because of the round of error. We're going to continue with the same question in the next part. And again, we have the same table. This person is a female and favors the tax increase on rich people. First and foremost, the only time the sample space shrinks when you have a given, you have a conditional probability. So no matter what the denominator is still the total size of 100. And we are going to use the formula probability of F intersection T is N of F intersection T over N of S. So the denominator is 100. It's an AND statement, intersection of events. Intersection of events. N of F intersection T. These are the females. These are the T or in favor of tax increase. What's in common? If you were to draw a line here and a line here, they come together at 22. So 22 is in common between the two groups, 22 over 100. The rest you simplify and it's very straightforward. This person opposes the tax increase on rich people or is a female. So this is called union of events. And for the union, probability of A union B is probability of A plus probability of B minus probability of A intersection B. That's a formula. It's also called the addition formula. And I hope you understand why we take off the intersection, because this is part of A as well as part of B. So we don't want to account for it 2 times. In this case, the person opposes the tax increase. That means this group A, or is a female, that means this group. So the probability of A union F which we can write it in this format, followed by the way, probability of A is N of A over N of S. So N of A over N. This is N of probability of B is N of B over N of S. So N of F over N of S and the intersection, which means the denominator is the same thing, namely 100. But over here, how many A's? Total of 33. How many F's? Total of 40. But how many are in common between the two? And that is 18. 18 is in common. Now, 18 is accounted for females as well as against. So it's been accounted for 2 times. That's why we're going to subtract that. The reason we subtract is because it's been accounted for 2 times, everybody. And it becomes 55 over 100. And of course, you can simplify. Are the events females and opposes the tax increase on rich people? Independent, explain. Well, probability of A given B is probability of A intersection B over probability of B. Probability of B given A is probability of A intersection over probability of A. I want to remind you that, okay? And I want to remind you of a couple of things when it comes to that. Probability of A intersection B, therefore, is the product of these two. Cross product, or the probability of these two. Okay, so probability of intersection of A and B is the product of these two or these two. So we have these two expressions. Independent events, the occurrence of one event doesn't change the probability of the other event. Probability of A given B is equal to probability of A. Probability of B given A is probability of B. And therefore, in this case, if we are talking about independency, probability of A intersection B becomes probability of A times probability of B. If independent. Okay. Now, why am I giving you those? Because I want you to know precisely the definition, and therefore, whether you say they are dependent or independent, you can justify it. So, this is the definition. Events, females, and opposes the tax increase on rich people are dependent because occurrence of one of the events does affect the other one. This is the definition of independence. It's extremely vague, and one may have a difficult time following that. But here's the proof using math. The two events, we look at their conditional probability. Probability of A given F, because remember, F stands for females, okay? Those who are opposing A. Probability of A given F. F comes after the given, so the total size now shrinks to 40. And how many of the F's are also A's? 18 over 40. Is this equal to probability of A? What is probability of A? 33 over 100. If they are identical, they are independent, but they are not. And that's the proof. What I'd like you to do as an example at home, take a look at this one. What is the probability of F given A? What is that equal to? And is this equal to probability of F? That's the second way. In other words, there are two ways to look at it. Probability of A given F equals probability of A. That proves independency. Or probability of F given A equals probability of F. That also proves independency. The next one is mutually exclusiveness. And again, it's the same thing. Whether they are this is the definition that they use. They are not mutually exclusive because a person can be both female and opposes the tax increase on rich people. How do you prove that? Numbers. Numbers. So you look at the probability of A intersection F. As you know, the probability of A intersection F, because it's the intersection, it's not a conditional probability. The total size is the sample space. How many are in common for A and F? Here's the A group, here's the F group, 18 over 100. Is it 0? If the answer is yes, they are mutually exclusive. Since the answer is no, they are not mutually exclusive. So you prove that with numbers. You always prove that with numbers, okay? And that's the beauty of math. We are continuing with the same question. Actually, we went over that. Okay, we went over that. It's just being repeated here. Here's the next question, everybody. Find the probability of getting the outcome of tails and 2 when a coin is tossed and a die is rolled. We assume independency. As you recall, the concept of independency, probability of A intersection B is probability of A times probability of B. In this case, the tails and 2 is probability of tails times the probability of 2. And again, the symbol, you could use the intersection of event here, which almost looks like an N. And so 1/2, the probability of tails, 50% or 1/2, probability of 2, there is 1 out of 6. And so the answer is 1 out of 12 precisely. A classic counting problem is to determine the number of different ways that the letters of personnel can be arranged. Find the number. First, can somebody read this permutation rule for us? Go ahead, please.
Permutations rule, distinguishable permutations. When some items are identical to others, the number of different permutations, order counts, when n items are available and all n of them are selected without replacement, but some of the items are identical to others, is found as follows. N1 are alike, N2 are alike, ... and K are alike.
So that's the formula. Thank you so much. This is the distinguishable permutation. So we're going to look at personnel. And we notice that it has 1, 2, 3, 4, 5, 6, 7, 8, 9 items, right? So n is 9. Then how many of each letter? P is 1, E is 2, R is 1, S is 1, so on and so forth. So according to this formula, this is what we get. And by the way, 1 factorial is 1, 2 factorial is 2. So the denominator is 4, and you plug it into a calculator, and you get 90,720 as the final answer. A box consists of 14 red and 36 blue markers. If we select 3 different markers randomly, what is the probability that they're all red with replacement? Well, if you look at the probability of red is 14 over 50 because 14 plus 36 adds up to 50. And it's 7 over 25 or 0.28. And since it's without replacement, it doesn't matter how many times we do it. If we select 3 or 5 or 10, it's with replacement. This probability remains unchanged. This is fixed because it's with replacement. So we put it back with replacement. So the probability of all 3 red, if we were to write it with the formula, would be R1 intersection R2 intersection R3, which is P of R1 times P of R2 times P of R3, and they're all identical, 0.28, therefore 0.28 to the power of 3, or 7 over 25 to the power of 3, however you write that, and the answer is 0.021952. So the key here, everybody, the key here is paying attention to with replacement. What is the probability that they are all red without replacement? Draw a tree diagram. First and foremost, even if they don't mention those statements, you really have to assume it's without replacement. So generally speaking, it is without the replacement. So let's see what happens. When you have 3 to pick up, the first one has the probability of the same thing, 14 out of 50. But the next one, remember, you've picked one is gone, so your sample space is no longer 50. That goes down to 49. And if one red is gone, 14 goes down to 13, and this thing continues. Okay, that's the concept. Therefore, in essence, it's the same thing here, but this is probability of R1 times the probability of R2 given R1 times probability of R3 given R1 intersection R2. And that is, again, the first one is the same, 14 out of 50. Look at the denominators. The denominators go down by 1, so 49, 48. The numerators also go down because we have 14 reds to begin with, but the next one doesn't have 14 anymore, but rather 13, and the next one is 12. And if you put it into a calculator, it gives you the answer, or you can simplify it as follows. If we were to discuss that with a second method, we can use combination of 14 over 3, combination of 50 over 3, or because we want all 3, 14 over 3, combination of 36, 0. In other words, from the red ones, the 36, we don't want to use anything. And this, by the way, ends up being 1. Okay, that's why if you don't write it, it's not a big deal. But the reason it may not be a bad idea to write it, because what if they said, for example, 2 red and 1 blue, then this one becomes 2, this becomes 1. The denominator remains the same because you're choosing 3 out of 50. And if you were to do your tree diagram, it looks like this. Notice, and this is extremely important. The first one, very straightforward, 14 out of 50, 36 out of 50 for the blue. And again, you want to keep it consistent, red versus blue. If the red is at top and blue is at the bottom, keep it the same for all branches. So over here, the second stage, all of them have the same denominator, 49. The denominator of 50 has gone down to by 1 to 49. Now, because this is a red branch, 14 goes down to 13. But because this is a blue, all 36 are intact. Because this is blue, all red are intact, 14, but the blue goes down to 35, and the same thing for the last stage. So I hope it's clear to everybody how we do the calculation. It's very straightforward, everybody. If the probability of winning is 5 over 12, what is the probability of losing? This is the concept known as complementary events, where probability of winning is given as 5 over 12, and I remind you of probability of A bar or A naught or complement of A is 1 minus P of A. So if the probability of winning is 5/12, 1 minus that is the probability of losing, which makes it 7/12. What are odds against winning? Well, the definition of odds are as follows. The actual odds against event A, O of A naught, is P of A naught over P of A. It is expressed as a form of A colon B or A to B, which both of them are integers. Odds are different than the probability. When the probability is extremely small, the two are almost the same, but there are two different things. So odds against, in this case, we want odds against the winning or odds for losing, which means probability of losing over the probability of winning according to this formula. Probability of losing is 7/12, winning is 5/12, and that's a complex fraction. The 12s cancel each other, 7/5, or you can write it in this format, or 7/5. That would be odds against winning. If the payoff odds is listed as 6/1, how much profit do you make if you bet $10 and you win? Well, let's look at the formula here. The payoff odds against event A is the net profit divided by the amount of bet. That is the formula, everybody. So this is a fraction. If you write it over 1, the two fractions are identical. Cross product must be the same. Therefore, the net profit times 1 makes a net profit is the product of these two numbers. Payoff odds, which is 6/1. By the way, this means, everybody, 6/1 or 6/1. Times the amount of bet, which happened to be $10. So if we put $10, we win $60. Could somebody read this question with parts A and B, please? Go ahead. Anybody is good. Go ahead, class. Somebody read it, please.
When two different people are randomly selected from those in your class, find the indicated probability, assume birthdays occur on the same day of the week with equal frequencies. Probability that two people are born on the same day of the week, and probability that two people are both born on Monday.
Perfect. We want to distinguish between the two. On the same day, that means any day is good. Okay, no particular day is specified. The first person can be born on any day. What really matters is that the second person have the same birthday. So that's the concept. So probability that the second person born on the same day is 1/7. Therefore, that's really the answer. So to have both of them have the same birthday, the first one can have any of those days. So it's 7/7. It's the other one that has to have the same birthday, and it's 1/7. And their product is 1/7. So again, on the same day, but if we specify the day, which it doesn't matter, by the way, it's Monday, Tuesday, Wednesday, a specific day, each of those two people have the same probability of 1/7. So the first person has a probability of 1/7 for Monday or any other day of the week. The second one has the same 1 out of 7 probability. Now, both of them born on Monday is their product, which makes it 1/49. So the key is the same day. That means any day is fine. But if you specify a day, then the probability changes. How many different auto license plates are possible if the plate has 2 letters followed by 4 numbers? So we are looking at how many spots? 1, 2, 3, 4, 5, 6 spots. We want 2 letters and 4 numbers. So 1 and 2 here and 4 here. How many letters? We have 26 and 26. So for the first one, if I were to write it out, I would write 26 here, also 26, because they didn't give me any restrictions. Numbers from 0 to 9, there are 10 digits. So simply put, 26 squared times 10 to the power of 4. Of course, it's a large number. You can use a calculator, but the key is to show your reader this method. 3 letters, no repeats, followed by 3 numbers, repetition is okay. Well, 3 letters, so that means 26, but we can't repeat, so it goes down to 25, then it goes down to 24, and then when we go to digits, it's 10 here, but it doesn't matter. The other ones can be 10 also, because we can repeat them. So 26 times 25, let me write that. So we have 26, 25, 24, but here we have no restrictions. So actually, let's write it here. Okay, and so we write it in this fashion. Four letters, repetition is okay, followed by 2 numbers, no repeats. So four letters. And then 2 numbers, 10, no repeats, therefore 9. 26 to the power of 4 times 10 times 9. 4 places, each character is either a letter or a number. So we have 4 spots. And we have 26 letters and 10 digits. That gives us 36 characters. And so I can put 36 here, 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 or 36 to the power of 4, because there is no restriction. In a first grade school class, there are 10 girls and 8 boys. In how many ways can the students finish first, second, and third in a foot race? Assume no ties. Understand we are looking at permutation and combination. So it's important to understand whether order is important or not. And so since we are interested in the first, second, and third, order becomes important, and therefore we are dealing with the permutation. We have a total of 18 students, and we want to choose 3, which is 18 times 17 times 16. Okay, that's another way of writing it. 3 spots. You can, the first, the second, there are 3 spots. And if you were to use a calculator, that's for the factorial, that's for the permutation. Enter the value of n, press math, select the probability, select NPR or NCR, enter the value of R. So 18 NPR3, that gives you the number. You don't have to do it by hand. So the answer is 4,896. Now, the girls finished first and second in a geography contest. Again, order is important. It's a permutation. However, we are only dealing with 10 girls. So N is a 10. And first and second, we want to pick 2. Permutation of 10, choose 2, or simply 2 spots, 10 times 9, because order is important, everybody. 10 times 9, which is 90. 3 boys be selected for launch duty. So order is not important. We just want 3 students from boys. So we want from 8, N is 8, N is 8, and we are choosing 3. So combination of 8, choose 3. And again, that is really telling your reader how you're doing it, which is obviously 8 factorial over 3 factorial times 5 factorial. And that's 56, or just use the calculator. You know how to use it now with the combination and permutation. We want to choose 6 students for a team, any team, in this case, a hockey team. And there are a total of 18 students. We want to pick 6. No, order is not important. We're dealing with the combination. So order is not important. We are dealing with the combination CNR. N is 10 plus 8, 18. And R, we want 6 of those, which is 18 factorial over 6 factorial times 12 factorial. And if you put it into a calculator, A18 NCR6 gives you the answer. You can put it there. Five students, we selected 3 boys and 2 girls. Again, order is not important. We just specify that from the group of boys, we want 3. From the group of girls, we want 2. So however that we choose them, then we multiply the 2. So from the boys, we want to choose 3. So CNR, combination of 8, choose 3. And CNR for the girls, combination of 10, choose 2. Their product is the answer. Again, you can throw it into a computer, into the graphic calculator, come up with the answer. 8 factorial over 3 factorial times 5 factorial. This is 10 factorial over 2 factorial times 8 factorial. And you plug it in and you come up with 2520. So that's really not a big deal as far as coming up with the answer. And I hope everybody is okay with that. Four girls be selected for a field trip. So order is not important. So we're talking about combination. N 10 R is a 4. So very straightforward, everybody. CNR, C10 4, which makes it 10 factorial over 4 factorial times 6 factorial. And that makes it 210. So I hope everybody is clear on that. It's pretty straightforward, everybody. In a lottery game, a player picks 5 numbers from 1 to 48. If 4 of the 5 numbers match those drawn, the player wins second prize. What is the probability of winning this prize? The probability of winning is n of winning over n of s. Anytime I deal with the probability, I like to know what my sample space. I like to know the denominator first. So I'm going to go with n of s, which is n of pick 5 numbers from 48. If I want to pick 5 numbers from 48 and order is not important, so it's simply the combination of 48, choose 5, which is 48 factorial over 5 factorial over 4 times 48 minus 5 or 43 factorial. And this, of course, you can use a calculator, but n of s uses this formula. Combination of 48 choose 5. That's the denominator. Now, I'm going to go with the numerator. How many ways can we win? We can win as long as we have 4 correct and 1 incorrect. So 4 out of 5, that means combination of out of those 5 numbers, we can pick any 4, or there is not important. Order is not important. So I'm going to go with the combination of 5, pick 4. And the rest of them can be incorrect. Okay. For the 8 minus 5 means 43 incorrect. So from 43, I choose 1. So the combination of 5, choose 4. That's the number of correct ones, 4 correct ones. Combination of 43, choose 1. Why 43? 48 minus 5. And we want 1. And so this is the numerator, and this is the denominator. Now you can use a calculator to come up with that. This is 5, this is 43. By the way, the numerator is very straightforward, everybody. Okay. The denominator, use a calculator, you simplify. However they want you to answer it. You can answer it with a decimal, you can answer it with a fraction, whatever they ask you. I am just writing the fraction. And if can be simplified, you can simplify. This is a similar question. A poker hand consisting of 5 cards is dealt from a standard deck of 52 cards. Find the probability that the hand contains exactly 2 face cards. Well, again, I want to know my sample space. Okay, I have 52 cards and I want to pick 5. Okay, so the probability of 2 face cards is n of 2 face over n of s, and I'm interested in n of s first and foremost. So the probability of 2 face cards is n, that means however many 2 face cards, over n of s. So first and foremost, this is a combination, or there is not important. N of s would be n of pick 5 cards from 52. So how do we pick 5 cards from 52? It's combination of 52, choose 5, which is 52 factorial over 5 factorial times 52 minus 5, or 47 factorial. Now, to get 2 face, okay, remember there are a total of 5. So it's n of 2 face means n of 2 face cards, and then the other 3 are non-face cards. Jack, Queen, and King. Those are the face cards. So we have 3 of them. We have 4 suits. So we have 12 face cards. And the rest of them, 52 minus 12 for the non-face cards. So this 3 times 4 suits gives us 12 face cards. And this is for the non-face cards. So as far as the numerator, how many face cards do we want? 2 face cards. So we're going to pick 2 out of 12. So combination of 12, choose 2. And the rest of them, combination of 40, choose 3. Because why 3? Because we have 5 cards. 2 of them are face cards. 3 are non-face cards. That becomes the numerator. Now, you have to put each and every one of them into a calculator, simplify it. This is 66, this is 9880, this is, let's see, 3 and 3, 2,598,960. And you simplify and you end up with 209 over 833. Sometimes it's not easy to do it as a fraction, but it is up to you how you deal with that. Could somebody read this last question for us?
A factory received a shipment of 16 sprockets, and the vendor who sold the item knows that there are 7 sprockets in the shipment that are defective. Both the receiving foreman accepts the delivery, he samples the shipment, and if too many of the sprockets in the sample are defective, he will refuse the shipment. If a sample of 7 sprockets is selected, find the probability that all in the sample are defective.
Excellent. Again, we are dealing with the probability n of all defective. That means probability of all defective. That means n of all defective over n of s. So first, let's discuss n of s. We have 16, and we're going to choose 7. That's the denominator. Now, out of 7 defect, we're going to use all of them. So combination of 7, choose 7. The rest of them from non-defective. So of course, from 9, 16 minus 7. From 9, we choose 0. So first, pay attention to the denominator, C16, 7. This is the sample space, because out of 16, we are going to choose 7. This is because we want all of them to be defective. And this one, remember, 9 is 16 minus 7, class. Now, of course, you put it into a calculator. For example, the bottom becomes 11,440. You should know this number is 1. So is this number. You don't really need the calculator, but you can put it into a calculator. C77, C90, those are both the same. The second method, you have 7 spots. Seven out of 16. The very first spot, what is the probability that the first spot is a defect? 7 out of 16. What about the second one? This is independent, without replacement, 6 out of 15. What is the next one? 5 out of 14, 4 out of 13. Notice the numerator is 16 and it goes down by 1, the denominator. And the numerator is 7 because we want 7 and it goes down by 1. And if you calculate it in this manner, you should get the same answer. Now, the same question, but this time we want to find the probability that none are defective. So if a sample of 7 sprockets is selected, find the probability that none in the sample are defective. So we're going to go with the same formula, and the top we're going to put n of non-defective. So the denominator remains the same, C of 16, 7. So the denominator, we have no problem with that. But look at this one. What happens in the numerator? We wanted 7 out of 7 to be defective. Now we want 7 out of 0. So C7, 0. And this one is C9, but we want all of them to be non-defect. So I hope you see that this number changes to 7. So how many defects? We don't want any. Combination of 7, choose 0. How many non-defect? All of them. So how many are left? 9 are left from the 9. So I want to make sure we understand that. 16 minus 7 is 9. That's how we get that number. And so C9, 7, you throw it into a calculator. This one, you already have it, okay? This one, you already have it, is 1. By the way, C7, 7, C7, 0 makes no difference. This one, you have to calculate, okay? So when you calculate that, from the 9, you choose 7, you get 36. So 36 over this number, and you simplify to 9 over 28, 60. The second method. None is defective. So the first one is 9 out of 16, right? The second one is 8 out of 15. 9 out of 16, 8 out of 15, 7 out of 14, and it continues, and it gives you the same answer. This one, class I. Meant to put this one, my apologies. So 9 out of 28, 60, two different ways.